draw real approximations. Very often in a free body diagram, your object comes down to a simple cube, simple square, or a simple cylinder or something. Remember in physics we like to approximate things, hence the Fermis. We want that object to, when it says position the object accurately, if you are drawing two free bodies and you're showing two things interacting, you don't have to do to scale, but you want to be within reasonable scale. Okay? Then you're going to start drawing forces. This becomes real important. When we were doing motion vectors, I tried to always model not drawing the line showing motion coming out of the middle of the object. There's a reason for that. So when we draw forces on a free body diagram, we always show them originating from the center of the object. And that's a concept called center of mass that we'll get to in about chapter 6. So in this case, this is some object, U, sitting in a desk, and we're just doing a free body. We're not showing the desk, we're not showing the floor, we're not showing all that other stuff. We're just showing U. And we've labeled one downward force arrow. So what would that force be? Gravity. So we're going to label it F sub G. Okay? We will have F sub this and F sub that and F sub this, that, and F sub a couple other things, which leads to all kinds of interesting little physics jokes. Okay, you want to label the magnitude of that force if it's known. So let me ask you this, and we will talk a whole lot more about this in section 3 of this chapter. What's the magnitude of the force of gravity on you?
Since acceleration is is it your mass?
It's your mass in kilograms times gravity, times 9.81. So, the force of gravity on you is going to be a positive or a negative number? Negative, because you're being attracted to the center of the earth. Okay, so we would typically label this. We're going to give you an imaginary mass of 50 kilograms. So, this would equal mass times acceleration. We're going to say you have a mass of 50 kilograms times negative 9.81 meters per second squared. Yeah, I know. Do you want me to make you weigh 100 kilograms? We'll double your mass. Just to make the math easy. Oh, good Lord.
Go back to 50. Just do
You know
both
what?
ways.
You can all have different numbers. You all have different masses, you realize. Normal mass of a human, 50 kilograms would probably be a low weight normal adult. I'd have to do. I can't do the conversion in my head. I know I'm 1.6 meters tall, but I can never remember my mass in kilograms. Okay, so we're gonna talk a whole lot more about this in section 2. But there's this funny thing that if a force doesn't have something balancing it out, things start to move. That's that whole mass times acceleration bit. So if the force of gravity is the only thing acting on you, guess what? You are plunging towards the center of the earth. So if right now the desk was to disappear, the ground under you in a straight cylindrical column was to disappear all the way to the center of the earth, woohoo! You're in for a ride. You're now accelerating at negative 9.81 meters per second squared towards the center of the earth. So clearly there's something else acting on you here, yes?
Yes.
Yes. As long as you're not accelerating up or down, you're just staying right where you're at. You're not rising up into the air. You're not plunging towards the center of the earth. We know that whatever force is acting in opposition to gravity has to be equal to it. Gesundheit. So what is acting on you? Forces. Yeah, your seat. Your seat is supporting your weight, your mass. So we have a force in opposition to the force of gravity, and you want to draw these as approximately, you want to get them as close to a scale by eye as you can. You don't have to use a ruler, you don't have to, you know, be very precise about it, but you don't want to have them look real crazy either. Yeah, be a little bit shorter. Okay, this one again, which we'll talk a lot more about in section 3, is called normal force. So it's the force that opposes gravity. It's F sub n. And as long as this object, U, is not moving up or down, Fn is equal to the negative of Fg. It's just opposite to Fg. That is your first free body diagram. The first of many, many, many to come. Okay? So let's move on to the next idea.